Hello, my name is Martin Pike, and welcome to this lecture from the Ada University course on mixed language programming with Ada and C++. Together we shall complete a series of slides, and then you'll be assessed on your learning using some quiz questions. During this lecture we will encounter advanced Ada subjects like tag types, anonymous access types, limited types and interfaces. It is a good idea to familiarize yourself with these subjects before continuing. Likewise, this lecture material is most relevant to the GNAT and G++ tools, as opposed to general Ada and C++. This lecture will show the pragmas and conventions that are supported by the GNAT compiler to deal with the subtle differences between interfacing with C and C++ with Ada. A subject that is heavily linked with C++ interfacing is name mangling, for which an overview is provided along with several approaches to dealing with it when interfacing Ada and C++. And while it's possible to interface to both subprograms and memory objects in C++, the real power comes from being able to support interfacing to classes. The lecture will also cover how to make use of C++ class constructors and Ada 2005 interfaces for multiple inheritance of abstract classes. We will also look at how Ada tag types can be exported to C++ main programs, and how Ada main programs can handle C++ exceptions. All code examples throughout this lecture are based on the Ada 2005 standard. The GNAT compiler supports a specific convention for mixed language programming with C++. They are CPP, or the word C_++. The example code here is an Ada main program declaring two imported C++ subprogram entities. The import pragmas show the use of both C++ convention values. An important aspect of this subject is ensuring the correct C++ entity names are used by Ada. The C++ language standard creates a need to resolve unique names for programming entities. This need is met by a technique called name mangling. There isn't a standard scheme by which even trivial C++ entity names are mangled, and it is possible different compiler vendors or even different versions of the same compiler or the same compiler on different platforms mangle public symbols in radically different and thus totally incompatible ways. Here is an example piece of C++ code that declares two functions with the same name and return type but different parameters, along with an integer memory object explicitly initialized to the value 30. Beneath the code is the C++ command line used to compile it into an object file called cpplib.o. To see the name mangled entities, we have to use the nm command, passing it cpplib.o. The nm output shows various pieces of information, but most importantly it shows the C++ mangled name. This is the name that must appear in the link name argument for the pragma import. However, basing your Ada source code on the C++ mangled name is not ideal and can present a maintenance problem or indeed cause incorrect foreign language entities to be used by Ada. But thankfully, there are several ways to work around this that we will go over now. It is possible, given the output from nm, to hard code the entity name in the link name parameter of the pragma import. Here we show two imported C++ subprogram entities. The link name parameter has had to be used to hard code the C++ entity name. If an unknown name is used, the build process is likely to fail at link time. However, there is a far more sinister error waiting to happen. The second snippet of code on this slide shows the same imported C++ subprogram entities, but with the incorrect link names. This code compiles and links, however at runtime it is impossible to know what will happen. Maintaining hard-coded C++ entity names not only increases maintenance costs, but also introduces a dependency on a particular compiler's mangling scheme. A C++ compiler vendor is under no obligation to maintain the same scheme, and a simple increment of the version number in the compiler used in your build system could bring with it untold consequences. A C++ compiler is free to use a mangled name even for a plain old C entity such as a constant, variable or subprogram, regardless of whether any C++ constructs like classes have been used. Extern C is meant to be recognized by a C++ compiler and to notify it that the noted entity is or to be compiled in a C style. Given the C++ code on this slide and the command line call to G++ and NM, we see that getRefWithString has compiled without a C++ mangled name. This allows the subsequent Ada main program to import getRefWithString using the CPP convention, but without having to use linkname. Whilst this does allow a mixing of C++ programs with mangled names and C subprograms without mangled names, this isn't really a viable solution when it comes to importing C++ classes. The most widely used approach to dealing with interfacing with C++ is to use the fdump Ada spec option for the G++ compiler to build the boilerplate code for you. This ensures the link name strings are all accurate given the version of G++ and means plain data, subprograms and classes can be imported. Here we see our familiar piece of C++ code and the command line used to generate the subsequent Ada package specification, albeit some code has been removed for clarity. Using fdump Ada spec is the preferred method of interfacing to C++ from Ada, and as the lecture introduces more advanced C++ code, the output from the fdump Ada spec option will increase in complexity. It is worth spending some time to review the features of Ada limited types, as they are used extensively in the code generated by fdump Ada spec. When a type is declared limited, this means that objects of the type cannot be assigned values of the same type. Additionally, there is no predefined equality operation for objects of a limited type. Also, the unique identity of an Ada object is retained, meaning once declared, a name of a variable of limited type will continue to refer to the same object. To be clear, the value is not constant as it can itself be changed. It just cannot be used in an assignment statement to another object. The desired effects of declaring a type limited when interfacing to C++ is to ensure the prevention of shallow copying. The Ada code on this slide shows how a limited record type is used to represent a C++ class and is then imported using the C++ convention. On the following slides, except where useful, with and use clauses will be omitted, pragma import and export will be omitted, only bound subprograms of interest will be displayed, and nested packages generated by the binding generator will also be omitted. Full examples will be provided along with the course. Here we show a concrete C++ class definition from which objects can be instantiated. It is called a class and has a private character attribute and a protected character attribute. The constructor accepts a pointer to a string, and there is also a destructor. We see the command line call to G++ with the fdump Ada spec option specified, and at the bottom of this slide is the resulting Ada package specification. The child utility packages of interface.c have been synthesized to provide a consistent interfacing type model even for C++. The attributes of the A class are represented as Ada record elements in a limited record that is imported using the pragma import CPP convention. The delete A class destructor is imported by identifying the link name argument for the pragma import. This is safe to do as the link name was determined by G++ itself, which knows how the mangling is to be performed and therefore removes the possibility of error. Here there is a brief introduction to a new pragma called CPP_constructor, which is specifically used to identify class constructor subprograms. Here it is used for the A-class constructor. In a build environment, it is likely to see fdump AdaSpec used routinely to ensure the package specification is an accurate representation of all C++ code. The CPP_constructor pragma is applied to a designated subprogram. The presence of this designation informs the compiler that the subprogram must be called whenever any instance of the A-class type is allocated. The compiler will automatically insert a call to this subprogram immediately after the instance is allocated. This can be seen by applying the "-gnat G compiler option and observing the intermediate code output. The link name argument to the CPP constructor pragma specifies the mangled name for the subprogram. Please observe the supplied example output here from applying the gnat-g option. The line after the instantiation of x is a call to the subprogram using the mangled C++ name of the class's constructor. This was inserted by the compiler automatically and is similar to what a C++ compiler does with default constructors. The Ada package specification shown in this slide came from running G++ with the fdump AdaSpec option using a particular C++ header file. The class has two constructors, a default one and one with a specific string pointer parameter. These have been represented by the new _A class subprograms imported using the C++ constructor pragma. Please assume that the default constructor assigns the value b to the attribute first character, and the constructor accepts a string pointer assigns the first character attribute with the first character from the supplied string. There is a representation of the class's destructor plus a publicly available subprogram called getFirstChar that returns the first character attribute. An Ada main program is now free to instantiate objects from this representation of the C++ class. An example of this is shown in the Ada main program at the bottom of this slide. The access type object X points at a new instance of A class created by calling the new _A class constructor, passing it a new string. The getFirstChar subprogram is then called against the X object, and the result of which is passed to the putLine subprogram. The output from this Ada main program is therefore the character B. It is possible to extend a C++ class from within Ada. Here we see a C++ class called base with a default constructor, an inlined virtual function, and an integer attribute called f. An Ada tag type called base has been declared as a representation of this C++ class. It is tag limited to ensure no copies can be made, but extensions are permitted, and the attribute f has been represented by an aliased integer field. A factory style constructor has been declared called newBase, along with an Ada representation of the C++ virtual function p1. A type extension of base called child is declared in the extensions package, and note there is no mention of the parent class base having any association at all with the original C++ class. The child type adds its own attribute called f2, provides a concrete implementation of p1, and declares a factory style constructor. The implementation of the extensions package contains the constructor that returns an instance of the parent class newBase. The overridden implementation of p1 writes out the string p1 from Ada as opposed to the string p1 from C++, which is what would have been written out if the P1 implementation from the original C++ class had been executed. Dispatching is the term for calling overridden subprograms from instances of object that exist in a type hierarchy. The code on this slide builds on the code from the previous slide on extending C++ classes. First of all, we start off with a C++ subprogram called call from CPP that, given a pointer to a base object, will call the P1 subprogram associated with the object. There needs to be an Ada representation of this C++ subprogram, and that is provided in the top right corner of this slide. The Ada main program below declares its own subprogram called call from Ada that, given an object from the hierarchy rooted in base, will call the P1 subprogram associated with the object. A class-wide type called ACK is declared that can be used to allocate objects from any point in the type hierarchy rooted at the base type. An instance O1 and O2 are allocated using the ACK type, and they are explicitly typed to base and child accordingly and constructed by their appropriate factory-style constructor. Next comes the example of dispatching, where calling call from Ada with the C++ base and Ada child instances produces the expected output of the string P1 from C++ followed by P1 from Ada. Subsequent calls to call from CPP passing both allocated instances produces the expected output from the associated C++ and Ada subprograms of the string P1 from C++ and P1 from Ada. This example shows a truly powerful feature of object-oriented mixed language programming with Ada and C++. C++ abstract classes contain at least one pure virtual function, which is a virtual function with no concrete implementation provided for the class. Ada represents abstract classes that include either attributes or at least one pure virtual function using abstract tag types. The C++ base class has a pure virtual function called P1 and a non-pure virtual function with a default inline implementation. There is an integer attribute called f, so the associated Ada representation must use an abstract tag-limited record, as shown in the top right of this slide. The f attribute is represented as a record field, and the two functions are implemented as an abstract subprogram and a non-abstract subprogram. A class called concrete implements P1 from base and is represented in Ada as a limited new base with a null record, as it has no class-specific attributes. Two primitive subprograms are declared, one called P1 that represents the concrete class version of P1, and a second called P2 that is specific to the concrete class with an implementation in Ada. The second type of Ada representation for C++ abstract classes is specific to those classes that have only pure virtual functions. In this code example, I1 is an abstract class with only pure virtual functions, and it can conveniently be represented by the Ada 2005 interface type. The Ada representation for the top C++ example code uses a limited interface and two abstract subprograms representing the pure virtual functions from the C++ class. A second C++ abstract class called I2 is also represented as a limited interface with a single abstract subprogram for the pure virtual function. Now that we have two Ada interfaces, they can be used to represent the C++ class that implements both the I1 and I2 abstract classes. So we arrive at having an Ada representation of the concrete C++ class that extends I1 and I2 and provides primitive subprograms to represent the implemented pure virtual functions. This concludes looking at how Ada and C++ can interoperate on both concrete and abstract classes defined in each other's syntax. We will now look at how Ada tagged types can be exported to C++ main programs. We start with an Ada package specification declaring a tag type called animal with a single field called the age, and the whole type is declared using the CPP convention. Two primitive subprograms are declared, one called new animal and the second called age, with both being exported using the CPP convention. The new animal subprogram acts as the tag type's constructor. The age subprogram returns a simple C convention integer. The package body provides implementation of these exported subprograms. New animal returns an instance of animal qualified with the value 20 for the age field. The implementation of the age subprogram returns the age field given an instance of the animal tag type. The header file animal.h contains a definition of the exported Ada tag type as a C++ class. You'll note the age subprogram has had to be declared as a virtual function. The C++ main program includes the animal.h header file, and then to avoid name mangling issues, it uses an extern C expression to wrap the exported constructor for animal objects and the Ada library initialization and finalization routines. The body of the main program then outputs the result of calling the age primitive subprogram of the animal tag type as an exported by Ada. The output from this program will be the value 20. It is possible for an exported Ada tag type to be extended with C++ code. However, this cannot be performed by way of type extension using inheritance. Instead, a method of embedding an instance of the Ada tag type in C++ classes must be used. Given the package alib and its exported entities to C++, it is possible to derive a new class dog in C++ from the animal class. The dog header file declares a new dog class but adds an instance of animal as a protected attribute. The constructor for the dog class uses the default initialization list to ensure the animal attribute is set to an allocated instance of the class. Here the dog class has a public subprogram called writeAge that uses the animal attribute to run the Ada subprogram that's implemented in Ada. The C++ main program creates an instance of the dog class and then calls its writeAge subprogram, which in turn calls the age subprogram on the embedded animal instance. While this approach isn't truly extending the animal class, it does demonstrate a method for embedding Ada classes in C++ classes. No lecture on interfacing to C++ will be complete without saying something about C++ exceptions. It is possible for Ada main programs to catch exceptions raised by imported C++ programs. The C++ implementation of the isOK subprogram deliberately throws an exception with an argument value of 20. The Ada main program here has imported the isOK subprogram and has declared a possible result value and has called isOK. There is a general Ada exception handler put in place, and in fact this is the only type of exception handler that can see generated C++ exceptions. On this occasion, the default handler will print out the string C++ exception raised, and on execution this Ada main program does indeed output the string as expected. We've now reached the end of the slides section of this lecture. You should now have enough knowledge of this subject to complete a small quiz, with questions designed to test your understanding. Each question is marked, and you will have a chance to review your score at the end of the lecture. Good luck with the quiz. The first question in the quiz imports a C++ subprogram as an Ada function entity called getRef. getRef returns an integer using the correct mixed language convention, and in this case the return value is assigned to a stack variable called x. Click on the tick icon if you believe this code is correct, or alternatively, click the line of code you believe is incorrect. You were right if you thought this code was incorrect. The string C++ is not a valid convention. The code at the bottom of this slide shows the two supported conventions, the strings CPP and C_+++ written in English. Question 2 presents a C++ subprogram called myfunc that returns an integer value 20. The Ada main program imports the C++ subprogram using the CPP convention as the function entity named myfunc. Myfunc is called in the body of the Ada main program, and its return value is assigned to a stack variable x. Click on the tick icon if you believe this code is correct, or alternatively, click the line of code you believe is incorrect. While this code will successfully compile, the link stage will fail. Unlike when interfacing with C, the external name argument for any imported C++ entities must take into consideration name mangling. Name mangling is a method that C++ compilers use to encode source code entity names to support features like overloading and virtual functions. In this example, if you ran the nm command against the cpplib.o object file, you'd see that there is no entity named myfunc. What you see is the mangled name. How you would interface to this subprogram is to use the link name parameter and specify the symbol name directly. Question 3 uses a slightly different piece of C++ code, but a familiar piece of Ada code to import the C++ entities. Click on the tick icon if you believe this code is correct, or alternatively, click the line of code you believe is incorrect. The answer is the code was correct. By using the extern C feature, the C++ compiler has been denied the right to mangle the name of myfunc. If you ran the nm command on the compiled object code, you'd see that a more conventional symbol name has been used without any mangling. Using the extern C feature provides a workaround for C++ name mangling. However, as you have seen in the slides, it is far from ideal. Question 4 brings us on to representing and using C++ abstract classes in Ada. The C++ base class has a pure virtual function called P1, a concrete virtual function called P2, and an instance level attribute called F. We want to represent this C++ class in Ada. Click on the tick icon if you believe this code is correct, or alternatively, click the line of code you believe is incorrect. The answer is no. The code is incorrect. The declaration of the C1 Ada type is wrong, as it has not identified the type as being abstract. The correct implementation is at the bottom of this slide. C++ constructors are vital to using the object-oriented features of C++ within Ada. This question uses a C++ class called A class, with a public default constructor and a public integer attribute. The implementation of the default constructor uses a default initialization list to assign a value to the attribute. The Ada main program has used a limited record to represent the C++ class and has imported its default constructor. An object of A class has been allocated on the stack, and therefore its constructor will be called in the compiled code. Click on the tick icon if you believe this code is correct, or alternatively, click the line of code you believe is incorrect. The code is in fact incorrect. Importing of C++ constructors cannot be done using the pragma import. The correct method is to use the pragma cpp_constructor. This code was in fact handwritten, and this kind of error can be avoided if the output from fdump ada spec is used. Question 6 shows a C++ abstract class with only pure virtual functions. The Ada representation of this class is shown below. Click on the tick icon if you believe this code is correct, or alternatively, click the line of code you believe is incorrect. The answer is yes, the code is correct. Ada 2005 provides the interface type that can be used to represent in Ada a C++ abstract class that has only pure virtual functions. Allocated instances of C++ objects can be used by Ada code like any allocated instance of an Ada entity. Here we see an imported C++ class along with a default constructor. Two instances are allocated with the value of the second instance being copied from the first. Click on the tick icon if you believe this code is correct, or alternatively, click the line of code you believe is incorrect. The code is incorrect. C++ classes are represented in Ada by limited record types, and because of the rules surrounding limited types, assignment statements cannot be used to copy instances. Question 8 uses a more complex example where an abstract C++ class has been extended and implemented by an Ada main program. The abstract class I_DDS defines a single C++ function called printme. The Ada main program has represented this abstract class using an interface type that has subsequently been extended in a subclass, and an implementation of printme has been provided. The body of the main program creates a new heap instance of the subclass and calls the printme subprogram. Click on the tick icon if you believe this code is correct, or alternatively, click the line of code you believe is incorrect. Well done if you selected yes, as this code is indeed correct. A key aspect of bidirectional mixed language programming is the ability for C++ main programs to use exported Ada tagged types. This allows C++ to use Ada entities in an object-oriented way. Please examine these code examples thoroughly and click on the tick icon if you believe this code is correct, or alternatively, click the line of code you believe is incorrect. This code is correct and provides a concrete reusable pattern you can use for using Ada tag types in object-oriented C++ programs. It is also possible to embed instances of exported Ada tag types within C++ classes to provide a method of type extension, albeit this extension is more of a has-a relationship rather than an is-a class relationship. Question 10 covers the subject of Ada main programs handling C++ exceptions. Given the example here, we have a C++ subprogram that will deliberately raise an exception with the value 20. The Ada main program imports this subprogram and also declares an exception to match onto this exception thrown by the C++ program. There is an exception handler for the C++ exception that will deliberately output the string C++ exception. Does the code fail to compile, run to completion and print out C++ exception, or does the program fail to complete at all? Please make your selection from the list and click the Submit button. The answer is the program fails to complete. The issue is that a non-default exception handler has been used in an attempt to handle the C++ exception. This is incorrect, and only default exception handlers should be used to handle C++ exceptions. Thank you for attending this lecture from the Ada Core University. I hope you have found it a valuable step in learning Ada and that you continue on to take other lectures. Thank you.